All right, so we are going to go over kind of the last example we have for two population hypothesis testing, which is when we have sample means and we only have sample variances. We'll also do it in Excel. So I believe where we left off was we had looked at how we do confidence intervals when this is the case. So start on slide 14. Basically, the steps are going to look just like what we were doing before with one population or with two population differences. Everything's the exact same. The only difference here is now our degrees of freedom isn't simply n-1. We said kind of has this really complicated formula, which I'm not going to make you kind of do, but I'll always give you kind of what that assumed true degrees of freedom would be, right? Or what it would be if you had plugged everything into that equation. Right? So our test statistic will look a little different, but it's going to look very similar to what you're doing with differences and means when we only had population variances. Okay, so it's going to look something like this. Remember, this is how we found our degrees of freedom. This is the one I said I'm not going to make you use, and I'll kind of always give you what this delta or what this degrees of freedom is. I'll kind of break this test statistic down just a little bit. I mean, it should look really similar to what we were doing before, right, with the differences in means, right? That's what we're interested in. We're going to subtract this assumed true difference, which we were kind of always using that zero value, so you can almost ignore that, right? Subtracting zero doesn't do anything. And then to get a test statistic, we always divide by the standard deviation of whatever statistic we're interested in. So that standard deviation would be the square root of each one of these kind of sample means distributions. So the sample variance over that group's sample size, and just add those two variances together. All right? So this is kind of like the variance of sample mean for group 1, variance for sample mean for group 2, add them together, and we'd have the variance for the difference in the sample means. Take the square root of the variance, that would give us the standard deviation. Right? So kind of the format of these test statistics is always the same. Take the test statistic you're interested in, subtract the assumed true value of that statistic, divide by the standard deviation. It's just that the standard deviations look a little bit different when we're doing these two population examples. Okay. So once we know that's kind of our test statistic, none of the other, once we have that, none of the other steps have changed at all. It's still just same kind of thing for hypothesis testing. So let's assume maybe we want to test for differences in salaries between gender to see if there's kind of any potential discrimination or kind of gender or wage gaps. So maybe I've got kind of male and female physician data. I take a sample of 41 male physicians, 41 female. I find the two sample means, and then I find the sample variances, right? So if I just want to test for whether or not male doctors earn a different amount than female doctors, what I'm really thinking about there is that mean for male physicians not equal to, right, anything different than the mean for my female physicians. When we set this as a hypothesis test, we have to have an assumed true value. We're not assuming values for the means. All we're assuming is, I'm sorry, my brain's not working right. Right? We rearrange this a little bit so that we're thinking about, is that difference anything other than zero, right? Or is that difference different than zero? So we've got a two-tailed test, right? And the reason why, just to kind of point out, I could have, so if this is my alternative hypothesis, the null is just the exact opposite, which is that this difference is equal to zero. So if this difference was equal to zero, these could both be 150,000, they could both be 180,000. I'm not assuming any values for what those means are. I'm only assuming a value for what that difference is. Okay? So we've got a two-tailed test here. Once we identify that null alternative hypothesis. And once again, just like with one population example, the other stuff we've looked at, when you see this term different, right? Are they different than each other? You should automatically be thinking not equal to sign the alternative hypothesis. Okay? So I've got this two-tailed test. The next step is what my critical values be. Right? So if we want to find a critical value for the 1% significance level, that's an alpha of 0.01. we've got this kind of assumed true degrees of freedom, where I'm giving you what the degrees of freedom would be if you had, used this equation. Okay. So how can we find these critical values? Well, right away, if it's a two-tailed test, which of these can I rule out? C, right? I know I have a pair of critical values. Okay. If I have a two-tailed test, I know that because I only have sample variances, I'm using those student t distributions. And with two-tailed tests, I have two-tailed such that the total area in the tails is alpha. So I want these pair of critical values. They'll be the exact same thing, or exact same value, but one's positive, one's negative, right? And I want alpha over 2, right? Because if alpha is total in the tails, and I have two equally sized tails, alpha over 2 is in each one, so 0.01 divided by 2. I want 0.005 in each tail. Okay. So I'll go to my student t-tables. Here we go. I want 0.005 in those tails. My degrees of freedom, I scroll down 80, 2.639. What if we remember, right? It's going to be negative 2.639 and positive 2.639. So if I have a two-tailed test, right, I'll divide alpha by 2, look that value up at whatever my degrees of freedom is, and that's how I'll get my critical values. When you think about our rejection region, anything in this range. Okay? So next step, if I have my critical values in my rejection region, I need to know, does my test statistic fall in that region or does it not? So the next step is calculating that test statistic. Right? So how would I find this test statistic? Well, it's that equation I had up there on the board. Really, once we identify the correct test statistic equation to use, which in this case it was differences in sample means, we only have sample variances. Right? This assumed true difference, I said we'll always keep it at 0, so that just kind of doesn't, goes away. Subtracting 0 doesn't change anything. So I look for the difference in those sample means, plug in my sample variance, sample sizes, and I get this test statistic of about 23. This is huge, right? Excuse me. So if we see a test statistic this large, right? I mean, we can prove this to ourselves, but if I plot this against my critical values, 22.9 or whatever it is way out here, really, really far into my tail, clearly in that rejection region. So what we're saying with that is, well, look, I assumed, we could kind of go back up here, and we had that assumed true difference of 0. I found something that was 23 standard deviations away from that assumed true value. So it's likely that the distribution isn't centered around 0, because if it was, it would be almost impossible for me to see the sample evidence that I found, or the difference in sample means that I found. So it's a lot more likely that the distribution is probably somewhere way over here. Right? So we're rejecting that assumed true value based off the evidence that we found. We can kind of think about the p-value approach here as well. I mean, if the area to the right of 2.639 was 0.005, what would the area to the right of 22.9 be? Pretty much 0, right? So if this area is pretty much 0, two-tailed test, I'll multiply by 2, but if it's almost 0 and I multiply by 2, it's still going to be almost 0. Right? So with a p-value of approximately 0, what levels can I reject at? Well, I only reject if the p-value is less than alpha. It doesn't matter what alpha I choose. If my p-value is almost 0, it's going to be less than that alpha. Right? So I'll be able to reject it like any level. Right? Even if I wanted to do 0.001, 99.9%, well, if my p-value is pretty much 0, I'm still going to be able to reject there. Okay? Any questions on any of that? I know I drew a little bit quick there. But like I said, once we have that test statistic, all the steps are pretty much what we've been doing, right? We've already seen how we do this with one population in terms of using that student t distribution. Nothing else will kind of change. Okay? All right. No questions on that? Okay. Oh, and then I always like this meme, right? I got 99 problems about rejecting the null ain't one. So anytime we think about having a really extreme test statistic, we can reject the null at any level, right? Kind of like in this example where the p-value is pretty much 0. Doesn't matter what level we choose, we're going to be able to reject. Right? So let's see kind of another example and how we would do this in Excel. Right? I'll show you a couple nice little kind of tricks in Excel as well. So I think this one, we'll go to that. Oops, looks like I forgot to delete one of my confidence intervals here. We'll go to that male data sheet, right? So I kind of didn't delete this, but I'll go over it real quick. It should be pretty easy. So I had it on a separate sheet, kind of female data, where I was finding the mean BMI of females, the sample variance of that BMI, and then the sample size by using that count function. Right? Over here on this male data sheet, I have all the male data separated, and maybe I want to test for whether or not there are differences between male and female BMI, right? So I kind of have my male data. I found the sample mean by taking the, using the average function, there.s to find my sample variance, and that count function to find my sample size. I then kind of use that trick where I can just say, okay, the female data is on this other worksheet, right? And if I copied that down, that's how I kind of got these other cell references in there as well, where it's referencing that other sheet. I didn't have to type this in, right? That was where I simply, if I go equals, click on the sheet and select the cell, hit enter, Excel automatically put that kind of in there for me. So that's kind of nice. Okay. So now I've got my 2 sample means, my 2 sample variances, and my 2 sample sizes. That's all the things I need to build confidence intervals and to do hypothesis testing for a difference in sample mean example. And very similar to what I showed you last class for the homework assignment, this will kind of is that crazy equation that finds the degrees of freedom for us. I already have that kind of built in there for you. So once we found the means, the variances, and sample sizes, this automatically computed my degrees of freedom. We said, well, it has to be an integer. And so then we always kind of floored it or rounded it all the way down to whatever the next closest integer was. So notice here, 6,459.8 becomes 6,459, as opposed to like kind of your normal rounding kind of rules of this would be rounded up. So we've got a nice setup here. So how do we do these confidence intervals? Well, if we go back to last class, even kind of using what we were doing with the hypothesis testing, right? Here's going to be our equations for the lower and upper bound. We'll take the difference in the sample means and then subtract and add our margin of error to get our lower and upper bound. So our margin of error is the t-value that gives us alpha over 2 on each side of the confidence interval at whatever our degrees of freedom delta is. And then multiplied by, remember this represented the standard deviation of the difference in sample means. So each group sample size over its, each group sample variance over its sample size. Okay. So the first thing we're going to do is just find those t-values that we're going to need. All right. So if I know the area that I want in the tail, and I want Excel to return to me that t-value, similar to what we were doing with the standard normal distribution, instead of norm.s.inv, we can use the t.inv function, right? So working in reverse, where we know the area in the tail that we want, and we want to find the t-value that gives that to us. So the area that we want kind of on each side of the interval, or the kind of think about maybe that as our tails, is alpha over 2, right? We want half of alpha above and half of alpha below our confidence interval. Comma, the next thing we have to tell it is what's our degrees of freedom? Well, this kind of makes it pretty easy. I already have it calculated up here. There's my degrees of freedom, right? Now, when I copy this down, right, for the kind of different levels of alpha or the different confidence levels, I want the alpha to change, right? That's the only thing that actually does change when we're building different levels of confidence. I want this degrees of freedom to kind of keep referencing the same cell. So I'll put dollar signs in front of the row and column heading there, and kind of now I'm good to go. Right, I'll freeze that so it keeps using that value. Now, remember, if I'm just using alpha over 2, it's always going to be, we're telling Excel the area to the left, right? Well, that is the value we want, but in our lower and upper bound equations, we kind of already have built in that positive and negative sign, right? So probably the easier way to do this is I just want the absolute value of that t-value. Because I want to go that many standard deviations below to find the lower bound, and that many standard deviations above to find the upper bound. Okay. Now, one thing that I want to kind of point out here, if we compare this to what we were doing when we had population variances, and we didn't need to use degrees of freedom because we're using the standard normal distribution, notice these values, 1.645, 1.96, 2.576, are very close. Like they're off to like the 4th decimal point from the standard normal values, standard normal distribution values. And that's because, look at our sample size, right? It's very, very large, right? So as your sample size gets higher and higher, the student t distribution that you're looking at is getting closer and closer to a standard normal distribution, okay? But nonetheless, they still are off to like the 4th decimal. You're still going to be getting slightly different values, okay? So to get our lower bound, we're going to take the difference between male and kind of female BMIs. That's what we're centering that confidence interval around. We'll then subtract the number of standard deviations we want to go away from that, or our t-value here, multiplied by the square root of each group's variance divided by that group's sample size. We'll add in the second group, so their variance divided by their sample size. And this should give us our lower bound equation, right? We're just using Excel to kind of be a calculator here. And the reason why that's helpful is because, you know, if I have to enter all these numbers in, like if I have these numbers written down on a piece of paper and I have to enter this in my calculator, I'm going to have to do this once to find the lower bound, once to find the upper bound, once to find the lower bound for the next level, and again to find the, you know, I'm going to have to be typing this thing in my calculator over and over. Well, in Excel, if I know that, you know, when I build these different levels of confidence, everything's going to be the same except for this t-value that I'm using, right? I'm using the same sample means, the same sample variances, the same sample sizes. So I will freeze those cells. So remember FN, F4, or if you don't have an FN key, just F4. And then on a Mac, Command T, I'll freeze those cells. The only one that I want to change when I copy this down is the t-value that I'm using, okay? So I hit enter, copy this down, have my lower bounds. We said our upper bounds is this exact same equation, so I'll kind of copy this, all right, go to my upper bound, paste it. The only thing that changes, instead of subtracting, I now add my margin of error. Right? Once I have that, now I can copy this down. It'll update my cell references, so it's using the kind of the new t-value, but because we froze all these cells, still using those original sample sizes, variances, and means. Okay? So now I've got my 3 confidence intervals here. Kind of notice, could I say that there's difference in male and female BMI? Well, at the 90% level, these only include negative values, right? So the way I set this up was male minus female. So if these are negative values, it means that females have kind of slightly higher BMIs based off the sample data that I found. With 90% certainty, I could say that female BMI is different than kind of male BMI, right? That difference is kind of a negative value, or that the true difference, you know, is negative. Now, I can't say that at the 99% level, right? Because here, now our upper bound kind of crosses over 0, right? It kind of, the true difference could be what? Negative 0.5, it could be positive 0.02, or it could in fact be that the true difference is 0, or that there's no differences in BMI between the genders, right? So I can't say that there's any difference with 99% certainty, okay? And, you know, one of the reasons why we can do this, and we'll kind of see this play out with the hypothesis testing, is, look, I found a very slight difference here, right? What's the actual difference? Male minus female. Negative 0.37, right? A very small difference in BMI. So that shouldn't be, right? If I'm assuming, right, what we kind of always assume, and here it was kind of test we had was that we wanted to know whether or not it's different from each other. So we're saying, is that difference, right, anything other than 0? Then our sample differences should be centered around that assumed true difference of 0. We found sample evidence that was pretty close to that, right? But remember, the standard deviation of this distribution, so the standard deviation of our difference in sample means, was this. And we had very high sample sizes from both populations, right? I'll go back and show you what they were. They were like 3,000 something. So as these get higher, what's going to happen to this standard deviation? It's going to get really, really small, right? If I'm dividing by very large numbers, this is going to get really, really small. So if I'm thinking about kind of this distribution, I probably didn't draw it really to scale. It's probably more so that it looks something like this, right? Where the only values that we're likely to see are really, really close to 0, right? So even seeing 0.37 is going to go against that assumed true difference, right? Any questions on that? Does that make sense? Okay. So that's why even seeing a very small difference that we did, we're still getting this ability with our confidence intervals to say, yeah, I can say that with 90 and 95% confidence, the difference is negative, right? Or that kind of female BMI is higher than male BMI. But I can't say that at the 99% level. So down here, let's do some hypothesis testing, okay? So we've got this assumed true difference of 0, right? We just want to see, are these things different from each other? To get our test statistic, all we're doing is taking that equation that we had and really using Excel to be our calculator. So in the numerator, we had the difference in these two BMIs, so male minus female BMI. We'll subtract the assumed true difference here, right? Now it is 0, so it's not going to change anything, but I can kind of show you what happens if we were to use anything other than 0. Divide by the square root of each group's sample variance, divided by that group's sample size. We'll add in the second group's sample variance divided by its sample size. Also notice it was about 3,500, those sample sizes, so they're very, very large. So we're just using Excel to be our calculator here. Okay. And we get negative 2.36. I could then find my critical values at different levels, which I don't know why this is so big. I'm going to switch. Can I do this? Hold on. Let me reshape this real quick. Why is it not? There we go. All right, never mind. I'm not going to mess around with this. Here, can I get there? There we go. So let's say I want to find my critical values. I guess I didn't give myself enough room here. I'm going to delete this just to give us a little bit more. So let's go alpha, critical value, p-value. So alpha 0.1, 0.05, 0.01, just so we can kind of make sure we see what we're doing here. So my critical value, right, is going to be the value that gives me alpha in the tail or in the tails if I have two tails. Here I have a two-tailed test, so I want alpha over 2 in each tail. This is literally, once we look at a two-tailed test, it's the exact same thing we were doing for confidence intervals. If we've assumed that that true difference is 0, right, this is going to be very similar for a two-tailed test what we were doing with confidence intervals. So I can use that t.inv function. I want, what is that, K19, so K19. I want alpha divided by 2 in the tail, comma, my degrees of freedom is up here. And once again, right, this will give us the negative critical value, which is fine, right? I would want to remember, maybe even give myself another column, right? That for a two-tailed test, I'm going to have two critical values. So here's the negative one. The other one will be that same value, but positive. So if I take the absolute value, that will give me the other critical value, which should be the same thing, but positive, right? I have pairs of critical values. Right? So it's kind of hard to indicate that in Excel. The best way to do that is put that you have kind of two critical values here, or even if you wanted to, if you don't want to do that absolute value, maybe next to it, type in something like this. Oops, doesn't like that, why? There we go. All right, positive and negative. Okay. Or right next to it, you know, plus minus, like in write the actual words out, whatever, however you want to like indicate that this is the value, but because it's a two-tailed test, you have a pair of critical values. We then copy this down. We wouldn't want the degrees of freedom to change, so we'll go back in, we'll freeze that cell reference. Now when we kind of copy this down, it's going to update alpha, but it's going to keep that degrees of freedom the same. Why is Excel being ornery with me? I guess I'm doing this. Right. So now we've got kind of our three critical values, and we have to remember. I'm deleting this. We have kind of pairs, right? Okay. So the next thing that we could find, you know, if we wanted to, I could use the critical value approach, plot my test statistic against these critical values and make my rejection decision. I kind of always think it's easier to like think about the rejection decisions using the p-value. So let's instead do that, right? So we have what, negative 2.36 was our test statistic. So once we found this test statistic, it's a t-statistic because we only had sample variances. So negative 2.36, the p-value would be the area to the left of that. But for a two-tailed test, it would have been equally as likely that I had seen something that far away from the assumed true difference, but above it. So once I find this area to the left, I need to multiply it by 2. So whatever this value is, multiply it by 2. So Excel will tell me what that area is if I use the t.dist function. The first thing I'll tell it is my test statistic, comma. The second thing I'll tell it is my degrees of freedom, comma. The last thing it needs is this cumulative? We'll always kind of use a 1 there. Okay? So tell it your test statistic, your degrees of freedom, comma 1. It'll give you the area to the left. Right? So my p-value is 0.009, but what did I forget to do? It's a two-tailed test, so I need that area, but multiply it by 2, right? So I get a p-value of 0.018 here. So what levels can I reject at? Well, I could kind of set this up like I did in our other example last week where we kind of used that if statement. So let's do 10% level, 5%, 1%. Oops, not 2%, 1%. If my p-value is less than alpha, which is what over here in K19, comma, if that's true, put in the word reject, comma, if it's not, put in that word fail to reject. Now, when I copy this down, I want it to update alpha to kind of line up with my significance levels, but I want the p-value cell reference to stay the same, right? That cell reference I don't want to change, okay? So now, and I could have looked at this and kind of said I can reject the 10 and the 5% because my p-value is less than 0.1 and 0.05, but I fail to reject this 1% level because 0.018 is, slightly above 0.01. Okay? But notice, these are the exact same kind of rejections that we made with the confidence interval. Now, the reason why, with two population examples, like this interpretation between the confidence interval and hypothesis test lines up a little better, is because now we're always using this assumed true difference of 0. So we're just looking to see, does our confidence interval include 0? If it does, then we would fail to reject that as a true possible value. If it doesn't include 0, like the 90 and 95% levels did, well, then that's a value that's outside of our confidence interval. So remember, the confidence interval is saying these are potentially the true values for this difference. So anything outside of that interval, we can say isn't one of the possible values. So we would reject those values as possible true differences. Well, here 0 isn't in the 90 or 95% confidence interval, so sure enough, once we do a hypothesis test on that difference of 0, we reject it because it wasn't kind of in that range of possible values. However, at that 99% level, it was in our confidence interval, telling us it could be one of the true differences. So sure enough, we fail to reject it as being a potential true difference, right? As an assumed true difference. Now, all of this kind of breaks down if we're not using a two-tailed test, because confidence intervals, we kind of have both sides. We're doing a right-tailed test. These don't quite line up. Also, if we're not using that assumed true difference of 0, it's a little bit different as well. Yeah. P-value. No, right? So remember, here's an easy way to kind of keep track of this. If I'm looking for a p-value, the area that I find, I multiply by 2. If I'm looking for a critical value, the area that I look up is alpha divided by 2. Yep. Because kind of think about it there. With a critical value, we start out knowing the total area in the tail. So then we have to break it down into kind of one side. Whereas with a p-value, I find one of those tails, I want to know the total area in both. And so there I have to multiply by 2. Yep. It's a good question. All right, so that should kind of complete this, right? I have an example down here. We won't work through it in class, but if you want to look at the completed file that's posted, it's just another example of a proportion example. So it's up to you whether or not, you can kind of look over that. We did, one over here on this South data sheet using proportions. So you'll have kind of, actually, no, where was that? Here, over here, doing proportions right here. So it's just another example looking at that, okay? Any questions on this before I keep moving? All right. So one thing that we could kind of play around with is, look, I am saying that I can reject that the difference is equal to 0 at the 95% level, which is really saying that there is a difference, right? If I'm rejecting that the difference is equal to 0, I'm saying I found significant evidence that there's differences in the BMI between the two genders, right? But I mean, if I start thinking about, can I say it's anything different than maybe 0.1, right? Assume that true difference is 0.1. Sorry, negative 0.1. Well, even there now, now I can't say that with 95% confidence. And can I say it's different than negative 0.2? I actually can't, reject that at any level now. So even though I did find that there is a difference, I can't reject that difference is, a pretty small value, right? Based off the sample evidence I found. Okay? But like I said, any example I'll give you, we'll kind of always use that 0 value to make it a little bit easier. Okay? So the other thing I want to show you, I'm going to drag this down here just so it's kind of standalone, is the shortcut to finding your p-value, okay? So this is awesome to save you some time, but I'll show you why you need to know how to find your p-value, and you're using your test statistic, and how you know how to do it without kind of using the shortcut first, because this shortcut has some issues, okay? So first of all, we can only use this t-dot test if we're looking at an example for the difference in sample means where we have sample variances, okay? So what we're going to do is we're going to select are two kind of columns of data for the two things we want to find the difference between. So for us, the first one was male BMI. So Control Shift or Command Shift on a Mac, hit the down arrow. Right, so kind of see it puts it up here, comma. The second thing was female BMI. So I have to go to that other sheet, select that, right? You can kind of still see your formula up here. Put a comma, go back to the male data sheet. Now, once I click on a sheet, excuse me, I should be able to see this, there we go. It'll put that sheet name in there. We don't really need that because now we're on that sheet. So you can leave it in there, but just to make it look a little cleaner, I'm gonna delete kind of that male data sheet reference because we don't need to see it. We're on the sheet again. I then will tell it how many tails are in this test, right? Well, I'm doing a two-tailed test, right? We had that not equal to sign, comma, and then it gives me three options. So the only ones that we're gonna use in this class are either gonna be option 1 or option 3. We haven't talked about matched pairs yet. So we're looking at a 2-sample example where we want the difference in those 2 samples that we took mean. So sample 1 was male BMI, sample 2 is female. And we have unequal variances, right? There's an option for equal variances. You can imagine this is very unlikely, right? Unless we're like literally taking 2 samples from like almost, I can't even, it's unlikely that we would have equal variances from whatever we're sampling from, right? So we'll use option 3, right? For what we were going to do on Friday, that was where we would use option 1, but we haven't got there yet. So what this essentially will do is this tells it, okay, these 2 columns of data you selected, calculate the sample mean, sample variance, and sample size for each one of these variables. That gives you your 2 groups, sample mean, sample variance, sample size. It then calculates a test statistic based off of the assumed true difference of 0. It then treats this as a two-tailed test, takes that test statistic, finds the area in one tail, multiplies it by 2, and spits out at you the p-value. So it basically did all that work behind the scenes of finding your test statistic, calculating the sample means, variance, sample sizes, finding the test statistic, finding the p-value. It did all that behind the scenes, right? Notice we get the exact same value. Okay? Now, why wouldn't I just first show you that? Well, first of all, it's nice that we understand the kind of steps to get there, right? These other functions in Excel. But the problem is this t.test, there's no option to change it to be any other assumed true difference other than 0. So notice if I want to test for other values, right? Like what we're doing, -0.2. Notice, well, now it's going to be way off in the p-value because there's no way to change the assumed true difference from 0. So although most of the time it's very useful because we often use 0 as that assumed true difference, in practice, you still want to know how you would find that p-value without just using that kind of shortcut function of t.test. Okay? Any questions on that? Okay? So it's kind of a nice little shortcut if we are using that assumed true difference of 0. Okay? Is there anything else I want to say in Excel before you? I think that covers it. So that should give you a lot more, allow you to kind of get quite a ways through that Excel assignment. Really the only thing left that we have to do for the Connect and the Excel assignment now is going to be matched pairs. So I think I'm just going to introduce the idea. We probably won't get through a whole lot of examples or anything today, but I'll introduce the idea of matched pairs, and then we'll kind of pick up on it next class and finish it. Right? So matched pairs is going to be a little bit different than what we've been doing when we look at the difference in sample means. Okay? We're going to actually only have one population, right? So it's kind of like we have 2 samples, but the samples are the exact same if you want to think about it individuals, right? It's just that we have a before and an after period, right? Now, it doesn't always have to be a time example. I think actually the example I show you in Excel will be a nice one where it doesn't just have to be like a before and after. you could be looking at, say, the difference between two variables within the same county, right? So kind of the example I'll give you, kind of start out explaining this with those so we can start to understand some more complicated ones. Let's say I don't know, I changed the workstation layout and I'm interested in, did the productivity of my 10 workers change, right? Or did it improve before and after the layout? Right? So what I could think about matched pairs is I have, and let's just use a worker ID so I can come up with some numbers. So I don't know. Right, I've got all these different workers. Instead of writing their names down, I'm just going to give them an employee number here, right, just to make it easy. So let's say whatever it is, the number of units sold, maybe we're at a call bank, right, and they're calling to, actually I just got a call the other day to give money back to my undergraduate institution. So like maybe this is like the number of people they convinced to give money to them, right? So some measure of productivity. So let's go, I don't know, make some numbers up here. Okay. Before we kind of rearrange this workstation, and after we rearrange it, I've got their after productivity. Right? What I'm doing with matched pairs is I'm looking at the same workers, right? Same 10 workers. Then what I'm going to do is I'm going to use some measure, right? This before and after productivity, and calculate what the difference was, right? So after minus before. So here we got 1, 3, -1, 2, and 4, right? That was kind of after minus before, or kind of the change in productivity, right? This person had sold 4 more units after this change, right? What I'm then going to do is take this difference variable, right? And I'm going to find the sample mean of that difference variable, right? What's the average of that difference variable? That's going to tell me what was the average change in productivity. So it's a little bit different because what we're not doing is we're not finding the mean of after productivity, the mean of before productivity, and kind of finding the difference between the two. We're actually saying, okay, no, we can calculate everyone's difference. What is the average change in productivity? Right? So it's a little bit different than what we were doing before. And it's kind of nice because we only have one sample here, right? We were recording multiple variables from that sample, right? But we still only have kind of one sample, same 10 individuals. So once I have that difference variable, right? I found the difference between this kind of first and second variable before and after productivity. I can easily find the mean of this difference variable and the variance of this difference variable, right? But once I have that, right, to build a confidence interval, I center it around, well, here, so I'll show you how we get to that, right? What we were doing before, when I had one population, I had one sample, and I only had the sample variance, and I was looking at sample means. This was the equation that we were using for confidence intervals. Well, now it's a little bit just notation because I still have one variable and I'm still finding a mean and have a sample variance. It's just I'm now indicating I don't just have like this original variable. I'm using a difference variable where I calculated this new variable based off of 2 other existing variables. But we still treat it the same way. It's still a mean, right? It's just the mean of a difference variable, right? So it looks pretty much the exact same. It's just that it's supposed to be a D. Now instead of a sample mean, we have a sample difference, and our variance is the variance of that difference variable. But other than that, it's the exact same thing, right? So there really is only one additional step from what we were doing with one population sample mean examples. And that additional step is, well, we had to calculate what that difference variable is. And that's really the only additional step. And so next class, I think what we'll do is we'll kind of go through some confidence interval examples for the sample difference. We'll go through a few hypothesis testing examples, and then I'll kind of show you what this looks like in Excel, okay? Because I think, yeah, you got 4 minutes left, so we'll get out a little bit early today. So we'll finish that up next class, matched pairs. Monday, what we're going to do is we're still going to meet in person. So if you want to show up on Monday based off of those of you responded that you wanted to, please show up. I don't want to do this for no reason. But we'll start linear regression, and then kind of after Thanksgiving break, we'll just kind of keep going through some linear regression examples, and really that'll be kind of the last thing that we talk about. Okay? So, other questions for me before we get out of here? All right, I'll see you guys on Friday.